let's talk about these two similar but different questions. So this first one here is asking us to just evaluate or find the definite integral from -2 to 2 of x cubed minus 4x. And we can do it the long way, but you might recognize that that function is odd, so the integral is going to end up equaling 0. Well, let's actually show it. We do this the long way. We're going to integrate, we're going to get x to the 4th over 4 minus 4x squared over 2 from -2 to 2. We're going to get 2 to the 4th, 4 minus 4 times 4 over 2 minus -2 to the 4th, which is also 16. So we're -2, so I'm going to put 16 here, over 4 minus 4 times -2 squared is also 16 over 2. So these end up equaling 16 over 4 minus 16 over 4 and -16 over 2 plus 16 over 2, which is 0. Or we could have said it's an odd function and the integral is from -2 to 2, so it's going to be 0. Graphically, what we have here is something that looks like this. And I know we've looked at this function before. I kind of want to talk about how the area between it and the x-axis is a different animal. So this function looks like this. With, it continues on, I suppose. And so what we've ended up doing is counting, bless you, right? That area gets counted as positive, and that area down there gets counted as negative. But if I actually wanted to find the area between the function and the x-axis, we should count both of those as positive. And so if we really want to do this and get the area between those two curves, we have to set this up in the following way. We're going to say, well, the area is going to equal the integral from -2 to 0 of x cubed minus 4x dx plus the integral from 0 to 2. There's a couple ways to do this. I personally would actually like to write it as negative x cubed minus 4 dx. Because from -2 to 0, did I have this the wrong way? I might have it the wrong way. Did I graph this wrong? No, I didn't graph it wrong. No. Now I'm like, oh, I forgot there's an x there. Sorry. Okay. From -2 to 0, this function is positive. If you plug in -1 minus 4 times -1 is positive. Whereas between 0 and 2, x cubed minus 4x, sorry about that, is negative. And so if we want to get the positive area, we can put a negative sign in front of it. Now, there's a little bit more going on here. What we're really doing is something that we're about to talk about in the next example. So I don't want to give it away just yet. But if we do this, we're going to get here x to the 4th over 4 minus 4x squared over 2. Let's simplify that. It's just 2x squared from -2 to 0 plus negative x to the 4th over 4 plus 2x squared from 0 to 2. And if we calculate this, this is going to be 0 minus 16 over 4 minus 2 times 4 plus, over here we're going to get negative 16 over 4 plus 2 times 4, which is 8, minus 0. And both of the areas end up getting counted as positive, right? This is a negative 4 minus 8, which is negative 4. And this is a negative 4 plus 8, which is a positive 4. So the area ends up being 8. So this area here is 4, and that area below is also 4. And we could do similar things to find the area that's between a curve and the x-axis. Let's look at another example, actually. So let's say we wanted to find patterns here. I'm going to find the area between f of x equal to cosine of x and the x-axis on the interval from, so let's go 0 to 2 pi. 0 to 2 pi? Sure, 0 to 2 pi. on, I should say, on the interval. I don't really need the from there. It's kind of extraneous. So the problem with a problem like this is that you have to know when the function is positive and when the function is negative, so that we can count the negative parts as positive. So we have to break it up. And really the easiest way to kind of see this, I think, is to graph it. So I graph cosine. I know that cosine of 0 is 1. And then at each subsequent pi over 2, so pi over 2, and then pi, and then 3 pi over 2, and then 2 pi, we go down to the middle, and then down to the bottom of the range, which is -1, back to the middle, back to the top, and then we're going to graph it like this. I will point out, because I think it's worth pointing out, that if you just did the definite integral here, right, if you just did the integral from 0 to 2 pi of cosine of x, what do you think we might get? Yeah, the area above the x-axis and the area below the x-axis are exactly equal to each other, so they're going to cancel each other out if we just do it as a definite integral. Because again, the definite integral is giving you the net area. It's the area above minus the area below. So to calculate the actual area, we need to separate the above parts from the below parts. Now, the way I did it in the previous problem was probably the least easy way of doing it. There's a slightly easier way, which maybe isn't my favorite, but it's perfectly fine, so I should be okay with it. So we know that from 0 to pi over 2, we're just going to integrate cosine. So our area is going to be the integral from 0 to pi over 2 of just cosine of x. And instead of making it negative cosine of x for the next part, what you can just do is break them all up. Oh, I said pi over 2, I wrote pi, sorry. You can break it up into all the different sections you need. So pi over 2 to 3 pi over 2 of cosine of x, and then plus the integral from 3 pi over 2 to 2 pi of cosine of x. And then instead of worrying about like which one is above, which one's below, we can put an absolute value around each of those definite intervals, so that whether the inside ends up being positive or negative, we're still going to count it as positive. So let's see what we get here. This is going to be the absolute value. Let's see, the antiderivative cosine is sine. So we're going to get sine of x from 0 to pi over 2, plus the absolute value of sine of x evaluated from pi over 2 to 3 pi over 2, plus, this looks kind of gross, the absolute value of sine of x evaluated from 3 pi over 2 to 2 pi. Okay, we'll write it out the long way. So that's going to be the absolute value of sine of pi over 2 minus sine of 0, plus the absolute value of sine of 3 pi over 2 minus sine of pi over 2, plus the absolute value of sine of 2 pi minus sine of 3 pi over 2. All right, let's see what we get. What's sine of pi over 2? Ooh, unit circle time. So pi over 2 is up here at the point 0, 1 on the unit circle, and sine is the y coordinate, so sine is going to be 1. So sine of pi over 2 is 1. Sine of 0 is 0. Sine of 3 pi over 2, you're at the bottom of the unit circle, and sine of 3 pi over 2 is -1, and sine of pi over 2 is 1. Plus sine of 2 pi is 0, minus sine of 3 pi over 2 is -1. So look at what we get. We end up getting the absolute value of 1 plus the absolute value of -2 plus the absolute value of 1. So if we hadn't had the absolute values there, you can see this would all add up to 0. 1 plus -2 plus 1 would be 0. But since we're taking the absolute values here and counting the negative parts as a positive area, because it's an area, we're going to end up with 1 plus 2 plus 1, which is 4. So the area between the sine function and the x-axis on this interval from 0 to 2 pi has 4 units. Also, just a quick aside, I think it's kind of just interesting that the area under a sine function happens to be like a positive integer. Right? It's not like something with pi or anything else. Like it's just 4 or 2. Like this area here in green is 2. Seems kind of weird to me, or at least maybe unexpected. So this kind of leads to the larger idea of finding the area between two curves. So really, another way I could have thought about this was, when I'm finding the area between these two curves, I'm kind of finding the, well, actually, let me not say it here. Let's actually look at another example, and then we'll talk about the idea that I really want to express. So let's look at examples here. So area between curves. And so now we're kind of getting into the depths of kind of the applications of integration, which will include like area, volume, maybe some moments of inertia, maybe some other physics stuff. Some of it kind of can be a little bit messy, but we'll talk about it all. So let's say we want to find the area between the curves y equal to x squared minus 2x and y equal to 3x. And normally you don't have to draw them, but it's nice to draw them and see what's happening. So let's graph both of these functions. So y equal to 3x is just a straight line that goes to the origin. You draw it like this. I know it would be normally looking a little steeper than that, but I'm drawing it so I can actually draw it nicely and get some good pictures here. And then y equal to x squared minus 2x is an upward opening parabola. And if you factor it as x times x minus 2, you can see that the intercepts are going to be 0 and positive 2. So this upward opening parabola is going to have intercept at 0 and 2. And it's look something kind of like this. And it doesn't have to be a perfect picture. I'm just trying to get an idea of how things look. And we can see that it looks like these two graphs intersect each other in exactly 2 points. And those 2 points of intersection are going to be our limits of integration. We're going to integrate from as far left as it looks like 0 to as far right as whatever that x value point of intersection is. So let's actually find where they intersect. So these are going to intersect, let's see, when x squared minus 2x is equal to 3x. Do the usual thing of bringing everything to one side. So let's subtract 3x from both sides and get x squared minus 5x equal to 0. Factor out an x. And then we can see that we're either going to get x equal to 0, which isn't surprising because we saw them both go through the origin, or x equal to 5. So this point up here is the point where x is 5, and whichever function you plug it into, you should get the same y value. So you plug it in here, 3 times 5 is 15. You plug it in here, 5 squared minus 2 times 5 is 25 minus 10, which is also 15. So here's the idea that we're going to employ. Just like before, when we've been finding or thinking about area under a curve as adding up a bunch of rectangles, we're going to do here. We're going to add up a bunch of rectangles. Now, we're not actually going to use the limit definition of the integral, although we could. What we're going to think about is we've got to find the area of this region here. I'm going to think about rectangles in that region. And so I'm imagining the region is filled with very narrow or skinny rectangles. All right, let's find the area of one of those rectangles. Well, if I look at this rectangle here, let's say we've got this one right down here, that rectangle, the area is the base times the height. The height, we'll worry about the base in a second here, but the height is, well, the height of that is just the top value minus the bottom value. So the height is going to be top minus the bottom. And the base, well, since it's a very, very skinny rectangle, the base is a very, very, very small change in x, which we could either call delta x, but I'm going to call dx. So this base here, dx, that's just a very small change in x. And the top minus the bottom is really just whatever the top value is, minus whatever the bottom value is. Now I'm going to say one more thing, which is maybe a little bit challenging, but the idea here is that we're thinking of this rectangle as just being located at some distance x from the origin, or from the y-axis, really. We've gone over x. X could be 1 or 2 or pi or any numerical value, in this case between 0 and 5. And whatever x happens to be, the height of that rectangle is going to be, well, it's going to be the top minus the bottom. So in this case, that actually is the top function, which is, well, looking at the graph, the top function is 3x, and the bottom function is x squared minus 2x. So depending on how far over we go, the height of the rectangle is going to vary from really, really small to moderately big to really small again. So for example, if x were to equal 1, the height of the rectangle would be 3 minus 1 minus 2. And 3 minus 1 minus 2 is 4. And if x were to be 2, the height of the rectangle would be 6 minus 4 minus 4, which is just 6. So depending on how far left or right we are, we get a different height. And the idea is we're going to, quote unquote, add up all the heights, all the areas of the rectangles. But instead of using a limit, we're going to jump straight to the definite interval. So we're kind of saying, oh yeah, I mean, I could say we're essentially adding up all the areas. So we're getting like the limit of the sum of the heights times the bases. That's going to end up being the integral from as far left as 0 to as far right as 5 of your heights times your bases. 3x minus x squared minus 2x dx. So very generally, the idea here is that if you're trying to find the area between two curves, we are doing the integral of the top function minus the bottom function. But really, 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 I want you to keep in mind this idea of we're really just taking kind of a representative rectangle here. The area of that rectangle is the top function minus the bottom function times the width. So again, there's your height, there's your width, or your base. Side. Excellent question. I was hoping someone would ask it. So one way to do this is graphically, but we don't always want to, or not always able to easily draw the graph. So if we don't want to draw the graph or can't draw the graph, here's what we do. We say, well, I know that these two functions intersect when x is 0 and when x is 5. And in between 0 and 5, one function is always above the other one. If it wasn't, they would intersect again. So pick any number between 0 and 5 you like. I'm going to pick 1. If I pick 1, pick x equal to 1, well, y equals 3x is going to end up being y equal to 3. And y equals x squared minus 2x is going to end up being y equal to 1 minus 2, which is negative 1. Which of those is bigger? 3, which means that function is the bigger function. So this will always work. If you're trying to find which function is bigger on an interval, you can just test some point in the interval and then see which of the two functions has the larger value, which is nice. So now we can actually find the area by using the second part of the fundamental theorem of calculus. So the area is going to be the integral from 0 to 5 of 3x, and I'm going to distribute the minus sign here and get minus x squared plus 2x. I would personally choose to simplify this before I integrated. 3x plus 2x is 5x minus x squared, and then we anti-differentiate. We get 5x squared divided by 2 minus x cubed divided by 3 from 0 to 5. We plug in 5, we get 5 times 5 squared over 2 minus 5 cubed over 3 minus we plug in 0. And here when we plug in 0, we're going to get 0 minus 0. Which I probably wouldn't do.
We could leave it like this. We could simplify it. It's not really very nice to simplify. This is going to be 125 over 2 minus 125 over 3. And instead of trying to get the common denominator right away, you might observe we could factor out 125. Let's say, oh, that's going to be 125 times 1/2 minus 1/3, which is going to be 125 times 3/6 minus 2/6. Not my favorite word to say, which is 125 times 1/6. But again, the simplifying here is not the most important part. The most important part is being able to set it up correctly and to differentiate correctly. And honestly, if you stopped right here, that's probably more than enough. Unless your professor says on the exam you need to simplify as much as possible. Questions about this example before we do quite a few more? Let's look at something like, sure. I'm not going to reference, that's fine. Okay, so let's find the area enclosed by the functions, y equals x squared, y equals 1 over x, and y equal to 9 in the first quadrants. So while you can typically figure out what the integral is going to look like if you have I should also actually back to your question. We'll go 1 second. So if you didn't know which one was bigger, you could kind of avoid the question altogether by saying, well, instead of figuring out which one's larger, I'm just going to do one of them minus the other one. And if I happen to have subtracted in the wrong order, put absolute values around them. So it is technically valid, although not everybody loves it when you do that, to say we could have instead maybe accidentally subtracted in the wrong direction, say the area is the integral from 0 to 5 of, instead of doing 3x minus x squared minus 2x, we might have accidentally subtracted the wrong way and done that. And then we say, well, it's wrong, but instead of having to write it again, let's just put absolute values around the whole thing, and then we're safe. Again, some people don't feel like that's a good way to do it, but it's not wrong. It is technically correct and is totally valid. So you can do it this way and be right. But now this next problem has an additional kind of thing to worry about, which is we're not just given 2 functions bounding this thing. I just forgot something. Something else? Oh, I didn't see it. Did you? Oh, you might want that too. Yeah. No worries at all. Sorry. No, it's all right. So here, since we have 1, 2, 3 things bounding our region, we really kind of do have to draw. Like it's just, and usually the functions are stereotypical enough, right? These are very common functions that we should know what they look like, but it's not terrible to draw. So let's draw this thing. So y equals x squared looks like this. Y equals 1 over x is the usual shape like this. I know I don't really need to draw the stuff on the left side because it said in the first quadrant, but it's still good to draw the thing. And y equals 9 looks like this. You can take a label things. Y equals 1 over x. Y equals x squared. So it is important here that we specified in the first quadrant because technically there are 2 different regions that are bounded by those 3 curves. There's this not correct region I want right here, because some of it lives in the quadrant 2, but the region I actually want is this one here, where that region is bounded by all 3 curves that we have been given and is in the first quadrant completely. So our job is to describe the area using an integral. And I'm still going to start off by thinking about adding up rectangles, but here there's kind of an additional thing to worry about, which is that depending on where I draw my rectangle, whether it's here or here, the top and bottom function aren't necessarily always the same thing. Well, I should be more specific. The top function is always the same in this picture. The bottom function is not. Over here on the left side of this region, the bottom function is 1 over x. On the right side, the bottom function is y equals x squared. And so to find the area here, we actually have to break this up into multiple integrals. Let me zoom in a little bit here. So here's how we're going to set this up. We're going to find that point of intersection first. So I need to figure out where x squared and 1 over x intersect each other. You could probably guess what the answer is going to be here. Anyone have any guesses for what x could be? With the solution to x squared equal to 1 over x? Yeah, this many, right? 1 squared is 1, 1 over 1 is 1. So sometimes, especially with these problems where you're finding where two functions intersect, they make the point of intersection relatively easy. Like you could guess it. You could also solve for it, right? If you multiply both sides by x, you get x cubed equal to 1. And then taking the cube root of both sides, you do just get x equal to 1. So either way is fine here. But that definitely has those cross at x equal to 1. I suppose we should also find these points of intersection because those are going to be our limits of integration. So setting 1 over x equal to 9, well, that's not too terrible. We can just take the reciprocal of both sides and get x equal to 1 over 9. And then setting x squared equal to 9. Well, technically the solutions would be x equal to plus or minus 3. Here's positive 3 over there. There's negative 3 over there. So we're going to get x equal to just 3 is the one we actually care about. So this point here is the point 3 comma 9. This point here is the point 1/9 comma 9. But now we have to break this thing up. And I think I should draw it again over here so we can get rid of that piece of paper. A little bit bigger. Here's the same region. And here are my two rectangles. Here's the first rectangle that we're going to find the area of. And here's the second one. The reason I'm emphasizing this idea is because this idea of finding a representative rectangle, or what I might call later a representative strip, is really useful when we start talking about finding volumes of revolution, as well as surface area and other things as well. So this idea is going to keep coming back again and again and again, which is why we're spending some time focusing on it right now. So what's the area of the rectangle on the left? Well, it's the height times the base. The height is just the top minus the bottom, which in this case is y equals 9 minus y equals 1 over x. I guess I could label those again. And the base is what? What am I calling the base? Every time. Every time I'm going to call the base dx. It'd be probably fine to call it delta x as well, but when we write the integral, we want to have a dx, not a delta. So that's why I'm using dx. And then for the green rectangle, the area of the rectangle is going to be the height, which is 9 minus x squared, times the base, which is also a dx. So then, for the black area here, it's going to be, I'm sorry, I should point out, these things look the same. This says, and I know my writing is not always lovely here. This says area of the rectangle, as does this. I know it might look like an area because the rec and the REA look very similar here. Sorry about that. This also is meant to say the area of the rectangle, A sub rec, whereas here I'm writing area. Apologies for any confusion there, because I can see how that would be confusing. The area of the black rectangle is going to be the integral from, so again, that value there is 1/9, 1, 3. So for the black area, we need to go from as far left as 1/9 to its far right is 1 of our base, sorry, our height times our base. And then for the green area, it's going to be the integral from 1 to 3 of our height, 9 minus x squared times our base, yes. And then to find the total area, we're just going to add those together. So the total area here is going to be the integral from 1/9 to 1 of 9 minus 1 over x dx, plus the integral from 1 to 3 of 9 minus x squared dx. Which then we should calculate. I will point out, and this is just a word of warning for future problems, on an exam, a lot of the time people will sometimes have you just set up and not calculate. So make sure when you're taking an exam, read the instructions carefully. Don't calculate an integral that you've only been asked to set up. You're just wasting your own time and not getting any points for it. So be careful when you're taking exams. Read the questions carefully. As Sarah likes to say, go slow to go fast. Read the questions slowly and carefully so that you can do the exam as fast as possible. All right, so doing this part here, the antiderivative of 9 is 9x. The antiderivative of 1 over x is the natural log of the absolute value of x, evaluated from 1/9 to 1, plus the antiderivative of 9 is 9x. The antiderivative of x squared is x cubed over 3 from 1 to 3. Then they plug in and we get 9 minus the natural log of 1 is 0, minus 9 times 1/9 is 1, minus the natural log of 1/9, plus, brackets around these things, plugging in 3, we get 9 times 3 is 27, minus 3 cubed is 27 over 3 is 9, minus plugging in 1, we get 9 minus 1/3. And there is no good reason I can see to simplify that any further. And I'm sorry, I was zoomed in a little bit. You guys probably couldn't see this picture that I kept referring to very well. If you can't see something that I'm referring to, please let me know. Sometimes I forget that I've zoomed in a little bit. So if there, yeah, I should zoom out a little bit. Sorry about that. Or we could do this a completely different way that's easier. So if I were given this region on an exam and asked to find the area, I probably wouldn't actually do it this way, even though it's totally fine to do it this way. Sometimes people will ask a very kind of subtly tricky question. I could have asked this question in the following way: set up an integral for the area bounded by these curves. And if I had written, sorry, where'd you go here? If I had written this answer, it would be incorrect because that is not an integral. That is 2 integrals added together. So someone, and it's not a very nice thing to do, but I've seen teachers do it in the past. If someone says write an integral for an area, they mean write one integral, which means we would have to do this one using a dy instead of a dx. Meaning instead of using vertical rectangles, we're going to use horizontal rectangles, which is really not that much different, but it might feel different the first few times you do it. So let's look at the same problem doing it the other way. We'll draw the region again. This time you can see it, hopefully. So once again, here's my region. I'll try to use the same colors from my curves because it's good to be consistent. So here is my 1 over x. Here's my x squared. And here's my y equal to 9. Okay. And also labeling these points of intersection. Here's the point 3, 9. Here's the point 1/9, 9. So instead of using vertical rectangles or vertical strips like we did in the previous example, now we're going to find the region drawing horizontal strips. So this horizontal strip or horizontal rectangle, whichever way you care to think about it. Now we're going to find the area of that. So the area of my rectangle Which is probably why I should use the word strip instead of rectangle, because it looks less like I'm writing the word area. It's still the same idea. It's still the base times the height. Or the height times the base. And in this orientation, here's my rectangle. We're thinking of the longer part as the height. So I'm thinking of this as my height and this as my base. So now my base isn't dx because it's not a small change in x. It's a small change in y, right? That's a little change up and down. It's a change in y. So my base here is really dy. And that's always going to be true when you're drawing a horizontal rectangle, is you're going to have your base being dy. We're going to be using dy. My height, instead of being the top minus the bottom like it was in the previous things. So let me actually say a little bit more about that. In the previous one, we're doing top minus bottom because we're doing the bigger y value minus the smaller y value, because you want to end up with something positive for your height. So here, I want to do the bigger x value minus the smaller x value. So I'm going to do right minus left, because bigger x values are on the right, smaller x values are on the left. So our height is going to be the right function minus the left function. So I'm going to write it the wrong way here. Don't write this down. We don't want to write this. X squared minus 1 over x times dy. The reason we don't want to write that is because that dy means when we do the integral, we have to integrate with respect to the variable y, the variable x. So what we have to do is we have to change our functions to functions of y instead of functions of x. So instead, we can see that y equals x squared becomes plus or minus the square root of y equal to x. Ooh. Which is it? Is it the plus root y or is it the minus root y? It's the plus because we're on the right side. But I will tell you, if we were on the left side over here, we would have to use the negative square root of y as our piece of the function. So be careful. Sometimes it's the plus piece, sometimes it's the minus piece, and you have to actually really look to know. And then, so here we're going to have x equal to positive root y. And then y equals 1 over x. If we solve for x, well, multiply both sides by x, divide both sides by y, x equals 1 over y. It is kind of interesting, just as a very, very side note, that 1 over x is one of the few functions that is its own inverse function. Like if you compose 1 over x with itself, 1 over x is just x. It's just kind of weird, but whatever. So here, x equals 1 over y is the left-hand side. So our area of our rectangle is actually going to be the right side, square root of y, minus the left side, I should say the right function minus left function times dy. And now we're ready to find the area of the region. So for the area of my region, we're going to do the integral from. So again, before, oh, sorry, so there's a question. I'll get to that question in a second. So before, we integrated from as far left as x equals 1/9 to as far right as x equals 3. And what I'm doing when I'm thinking about that is I'm thinking about being able to essentially draw this rectangle anywhere in between those two values. Or I actually like to think about the rectangle like sliding as far left and as far right as possible. I could imagine it as being like a little slider and just kind of moving left to right. Here, we're not moving left to right, we're moving bottom to top. So how low can I draw my rectangle? Ooh, I don't actually remember what the y value was there. Yeah, I mean the x value was 1, but also the y value is 1 because they happen to be the same. So we're going as low as y equal to 1 and as high as, how high? Yeah. So often, almost always, your limits of integration will be different values if you do it a different way. Occasionally you have some integrals where you get like the same thing either way because it's like 0 and 1 and 0 and 1, but a lot of the times they will change. So then we're going to get the integral from 1 to 9 of y to the 1/2 minus 1 over y. And it sure looks like this is a lot easier to actually calculate than the previous way we did it. So often setting this area up as one integral, if you can, versus two, is the better, easier choice. And there was a question, someone asked me, can you explain why 9 minus x squared dx, and same thing for the other area? Can you say why it's 9 minus x squared? Sure. So, sorry, that question was a little bit ago. So the reason why we did 9 minus x squared over here was because this height of this rectangle really was the top value of y equal to 9 minus the bottom, I should say the top function of y equal to 9 minus the bottom function of y equal to x squared. Similarly over here, the height of this rectangle is the top function y equal to 9 minus the bottom function of y equal to 1 over x. Because if you're trying to find the length of something, it's just the difference between the two values it has. So hopefully that offers some explanation. Calculating this, we're going to get y to the 3/2 times 2/3 minus the natural log of the absolute value of y evaluated from 1 to 9. And we get 2/3 times 9 to the 3/2 minus the natural log of 9 minus 2/3 times, I'm not going to write 1 to the 3/2. What's 1 to the 3/2? What's 1 to any power? Just 1. Right, 1 squared is 1, 1 cubed is 1, 1 to the 3rd is 1, the square root of that is 1, 1 to any power is 1. So when we have 2/3 times 1 to the 3/2, we should just write it as 2/3. And the natural log of 1 is 0. And these two answers should be the same. They might look a little bit different because the first one we didn't simplify is a bit more complicated. But yeah, those answers are going to be the same if we work it out. Or we're not going to work it out. I will say here, if I were doing this, I would probably do one more simplification because 9 to the 3/2 does simplify as 27. It's the square root of 9, which is 3, and the 3 cubed is 27. So I would probably write this as 2/3 times 27, which is 18, minus natural log of 9, minus 2/3. This one is also a lot easier to simplify, I would say. So there's usually a good reason to write this in kind of the nicer way, for lack of a better term. Questions? Yeah. Sure. Well, so again, so we're not saying top and bottom in this case, we're saying right and left, because we're thinking about, instead of doing the bigger y value minus the smaller y value, we're doing the bigger x value minus the smaller x value. And that's how we're figuring out which one it is. But again, and so here you really, so I would say you really kind of do have to draw this. Like I'm going to say there's not a lot of getting around drawing graphs in this class, especially when we start finding that's more 21C. When you start doing double integrals in 21C, there's a lot of drawing of the region of integration. So it is worth your time and effort to make sure you feel comfortable drawing graphs in 2 dimensions, because they're going to come up again and again and again, and you're going to need to be able to draw them relatively competently to figure out what's going on with your region of integration. Let's look at another example. Unless there's more questions about this. We'll do 2 more examples and then we'll take a breath. So we're just gonna, so let's read the instructions here. The instructions for this are: set up integrals or integral, a single or a double, depending on how we think about it, for the area between the function f of x equal to x to the 4th plus 16x and g of x equal to x to the 5th plus x to the 4th. A couple words of wisdom here is that this one I'm pretty sure I'm going to have to do in terms of x, because it would be pretty difficult to solve y equals x to the 4th plus 16x for x. Like there's no real way to isolate x here or here. So I'm pretty confident in them doing things in terms of x. I don't really have a good bead on drawing either of these things, but I don't think I need to. So again, if it's just the area between 2 functions, we can do the following kind of thing. So first, let's find the points of intersection. So we're going to set the functions equal to each other. So we're going to set x to the fifth plus x to the fourth equal to x to the fourth plus 16x. We're going to bring everything to one side. So the x to the fourth will cancel and we get x to the fifth minus 16x equal to 0. One quick word of warning here. If you were to instead do this, say x to the fifth equals 16x, it's really, really dangerous to divide both sides by x here. If you divide both sides by x, you're going to miss out on the fact that x equal to 0 is a solution. And we don't want to miss any solutions. So here, we really, really, really don't want to do any dividing by x. We want to bring everything to the same side and then factor as much as possible. So I can factor out an x to the fourth minus 16. I can definitely factor x to the fourth minus 16. It's a difference of squares. It's really x squared squared minus 4 squared. So that's going to factor as x squared plus 4 times x squared minus 4. And if you multiply that out, oh yeah, you get x to the fourth. The middle terms cancel, minus 16. And then x squared minus 4 factors as the difference of squares again. So you get x times x squared plus 4 times x minus 2 times x plus 2. So how many, show me on your fingers, how many solutions to this equation are there? See a few too many fingers sometimes. There are 3 real solutions, I should say. Okay, technically, if you want to be a little bit pedantic about it, technically there's 5 solutions here. X equals 0, x equals 2, x equals negative 2, and then this part has 2 imaginary solutions. But really, what I should have asked is how many real solutions are there? And there are 3, and we only care about the real ones because those are the ones that we actually graph. Imaginary solutions, imaginary numbers don't really come up in this class at all. That's for later classes, maybe. So here, our points of intersection are x equal to negative 2, x equal to 0, and x equal to 2. And the problem with that is, in each interval, we're not sure which function's on top. So I don't know what these functions look like exactly, but maybe one of them looks, and I'm just going to draw something that's not the right thing at all, but maybe one of them looks like, I don't know, something like that. And maybe the other one looks something like, I don't know, I'm going to draw a different color here to make this work. Yeah, kind of, sure. Maybe it looks like that. So like 2, they intersect there, 0, they intersect there, and then negative 2, they intersect there. And so from negative 2 to 0, one of them's on top. From 0 to 2, the other one's on top. But you know what? You don't have to be able to graph them to figure out which one's on top because we can just pick a number in each interval. So in the interval from 0 to 2, what number do you think I'm going to pick? Right. I mean, technically, there's a lot of choices. You can pick any number like 1.1 or 1.7 or 1.5 or other square root of 2, but we should pick the nicest number we can, which is 1. So if I pick x equal to 1, I can see that f of 1 is 1 plus 16, and g of 1 is 1 plus 1. So clearly in this interval, f is the larger function. In the interval from negative 2 to 0, I'm going to pick x equal to negative 1. And when I plug that in, f of negative 1 is going to be 1 minus 16, which is negative 15. And g of negative 1 is going to be negative 1 plus 1, which is 0. And in this interval, g is the larger function. So I'm going to set this up without using absolute values. Our setup is going to be the area is equal to the integral from negative 2 to 0 of, wow, that does not look like 15, of g of x minus f of x. And I will write those out in a second. Plus the integral from 0 to 2 of, well, from 0 to 2, f of x is the larger function. So it's going to be f of x minus g of x. And then we're going to actually write out what those are. So this is going to be the integral from -2 to 0 of g of x minus f of x. So x to the 5th plus x to the 4th minus x to the 4th plus 16x. If you were actually completing this problem, you would simplify that and write that as just x to the 5th minus 16x plus the integral from 0 to 2 of the reverse subtraction, x to the 4th plus 16x minus x to the 5th plus x to the 4th, which would simplify as just 16x minus x to the 5th. And if you subtract things in the opposite order, you should just get the negative of the thing you had before. All right. Let's look at one more area example, and then I'll switch gears a little bit here. So let's say, let's say we want to find or find the area enclosed by the curves f of x equal to the natural log of x, x equals 0, y equals 0, and y equals e. Okay, I got 4 things I got to draw. 3 of them are not that bad. And actually all 4 of them are. All of these are things we should be able to draw without too much trouble. I will point out that 2 of them I just drew. My x-axis is y equals 0. My y-axis is the line x equals 0. Be careful with this. Y equals e. Okay, look at me for a second. Y equals e is not this function. That's e to the x. We don't have e to the x. We have y equals e. We have y equals about 2.7. That's a constant. So here's my y equal to e. But it's really easy to get fooled by that and be like, I think you have y equal e to the x. So be careful there. And then natural log of x has the usual natural log shape. I'm going to draw it. So here's y equal to the natural log of x. There's an intercept at 1. There, it keeps getting bigger and bigger and bigger. Okay. So the region that we have described is this region here. Right? When you're talking about finding the area of a region bounded by a bunch of curves, each curve mentioned has to be a boundary. So what kind of rectangles am I going to draw? Yeah, question or answer. Horizontal. I could draw vertical, but it's the lesser choice. If I draw vertical, I'm going to have to use 2 different integrals. Although I will point out it's not that bad because the first integral is just the integral of a constant minus a constant. So that's really just the area of that rectangle. But the problem here actually is that, so actually I'm going to do it both ways to show you how doing it this way is also at this juncture something we're not able to do. Let me show you why. So if we do it vertically, so with vertical rectangles, well, we're going to get, I should find these points of intersection. So I said that was the point 1, 0. And this point here is where y equal to e and y equal to natural log. Ooh, e was not the choice I meant to make. Oh, well, such is life. It'll still be fine. It's just going to be less nice. So we set these equal to each other. Yeah, it's going to be really not nice. Oh, well. So you have e equal to the natural log of x. And then if you solve for x, you're going to get, yeah, that's terrible. E to the e equal to x. Sorry about that. We could change it, but it's not really that important. So that's the point. E to the e comma e. E to the e is interesting. I should have actually made that like 1, so that when you set natural log of x equal to 1, you got x equal to e, but I didn't. And I feel like I shouldn't just change it. So we'll live with my choice. It'll be okay. So vertical rectangles, this first integral is going to be the integral from 0 to 1 of the area of my rectangle is e minus 0 is my height times dx is my base. For the second integral here, we're going to get the integral from 1 to e to the e. And then we're going to do the area of our rectangle, which is our height, which is e minus the natural log of x times our base, which is dx. And here's the problem. We don't yet have the tools to anti-differentiate the natural log of x. The derivative of the natural log of x is 1 over x. The antiderivative of the natural log of x, we will eventually learn via integration by parts is equal to x times natural log of x minus x. But it does require a method that we don't have yet. So that's another reason why we can't actually do it this way. And we should really do it the other way. If we draw a horizontal rectangle instead, we're much happier about this because now we can say that using horizontal rectangles, well, we're going to go as low as y equals 0, as high as y equals e, and we're going to integrate the right function, which instead of saying it's y equals natural log of x, we're going to solve for x, and we're going to get x equal to what? If y equals natural log of x, how do we solve for x? Not one, I'm not taking a derivative here, I'm solving for x. So if I've got y equal to the natural log of x, what can I do to both sides of this equation that will help me isolate x? I can write both sides as e to the thing. Because e to the natural log of x is just x. So I have e to the y is equal to x. So my right function is e to the y, and my left function is x equals 0. dy. And look how much easier the integral is to do this way. What's the antiderivative of e to the y? E to the y, right? It's like the best thing ever. So we're going to get e to the y evaluated from 0 to e. And yes, it is weird that our answer is e to the e, but it is. We're going to get e to the e, and don't sleep on this. It's not just e to the e, it's e to the e minus e to the 0, which is 1. So be careful. Sometimes when you plug in 0, you don't just get 0. Sometimes you get other numbers. So you get e to the e minus 1. Cool. So I wanted to ask, sorry, so actually I want to ask questions about this. Things I could explain better. Yeah. So it was given to me that this horizontal line was y equals e. So that's how I got the upper bound. I was thinking about how low my my horizontal rectangle could go, which is as low as y equals 0. And the highest it could go was, well, we were literally bounded by y equals e. And so that's how we're getting e as our upper bound. Yeah. So in the last 20 minutes here, I wanted to kind of ask you all, is there anything that you would like to hear more about? Like kind of if going back a little bit, like should we say maybe more about the fundamental theorem of calculus part 1? Or maybe someone would like to see like a limit definition of the integral kind of question. Like are those things still things we want to be seeing, or are we done with that? And for that's for people on Zoom as well. Like is there anything you would really like to like see one more example of, because it's been a minute, but still like those things feel just not as maybe conceptually clear. Yes, fundamental theorem of calculus part 1 and part 2. So here's what I'll say. So I'm definitely happy to do that. But I'll point out, today we have used the fundamental theorem of calculus part 2 a lot, because in each of these problems that we've actually found the answer to, we have used the fundamental theorem of calculus part 2 where we have found the definite integral by first finding the antiderivative, like we did here, and then evaluating it at the endpoints. That is fully fundamental theorem of calculus part 2 all the way. We can do another example, but I just want to make sure that it's clear that we are, whenever we're finding a definite integral, we are almost always using, not always, but often, almost always, using the fundamental theorem of calculus part 2. Occasionally, you're going to use an area formula like a half a circle or an absolute value triangle kind of thing. But most of the time, when we're finding a definite integral, we are using that second part of the fundamental theorem of calculus. But let's go back and talk about a couple of examples with the first part of the fundamental theorem of calculus. Because I actually saw a really good question earlier today. Let's see if I can remember what it was. It was something like the following. Oh yeah, I know what it was. It was this. It was given that. Sorry, I have to think for just 1 second. I know what it is. It's just coming to me. Yes, here we go. Given that the integral from 1 to x of, let's make it fun, let's say secant squared of 7t dt is equal to f of x. Sorry, yeah. I think that's right, yeah. Oh darn, I can't remember what it was so good. I'm sorry, it made this person really have to think about what they were doing. But I think I've lost it. Given that, oh no, I know what it was. Sorry, sorry, you should scratch it out. Apologies. Let's try one more time. Here we go for real this time, I promise. Given that the integral from 1 to x of f of t dt is equal to, let's not make it secant squared, let's make it a little bit nicer. Let's make it say secant of 7x. Yeah, that's good. Find f of x. I think this is a really good question to test your actual understanding of the fundamental theorem of calculus problem. Because this question is easy if we know what to do, but it's not if we don't. I know that sounds like a dumb thing to say, right? It's easy if you know it, but I mean it's easy if you recognize that you can really easily apply the first part of the fundamental theorem of calculus. So the way we're going to find f of x here is by differentiating both sides of this equation. So if we take the derivative of the integral from 1 to x of f of t dt, sorry, f of t dt, what's the derivative of the integral of f of t? I should say all the things. What's the derivative of the integral from 1 to x of f of t? It's f of x. That's what the fundamental theorem of calculus says. If you do the derivative of the integral, you get back to the function you started with, but you're plugging in x instead of t. You could take a longer route here and say, well, I know that the antiderivative would be some capital F of t evaluated between 1 and x. And then I'd have the derivative of capital F of x minus capital F of 1. What's the derivative, using the usual notation where capital F is the antiderivative of little f? What's the derivative of capital F? I know you guys want to say it. It's little f of x. Okay, here's the, in my opinion, actually kind of harder part of this question. What's the derivative of capital F of 1? Yeah, because whatever f of x was, you plugged in 1, and f of 1 is a constant, and the derivative of that constant is 0. So look, the derivative of the integral from 1 to x of f of t is equal to f of x. So they said find f of x, which means take the derivative of this, but if you take the derivative of that side, you also take the derivative of that side. So the f of x is going to equal the derivative of secant of 7x, which is going to be secant of our stuff times tangent of our stuff times the derivative of our stuff. It's not a super hard question if we know what to do, right? Differentiating secant of 7x is not the hard part here. It's recognizing that you take the derivative of this to get f of x, and then that's just taking the derivative of that. That's a good question. So let's look at another one. let's look at the what I would say is a more straightforward one. So I want you all to try this one on your own. Find f prime of x given that f of x is equal to the integral from 2 to the natural log of x of sine of t squared times e to the t dt. Yeah, that's fine, sure. And I would point out, it's not clear, we can't anti-differentiate that. We're not being asked to, but this integral is not something you can actually find. You just have to apply the fundamental theorem of calculus without doing anything else. In case it's hard to read what I've written there, that says the integral from 2 to natural log of x of sine of t squared times e to the t times dt. I'm always happy to clarify anything I've written if it's hard to read. So let me point out, if we were given that g of x was equal to the integral from 2 to x of sine of t squared times e to the t times dt, the derivative of g of x would just be sine of x squared times e to the x. I'm gonna say one more thing, even though I'm gonna write this down. What I really thought about doing here was I plugged in x for each thing, and then I multiply by the derivative of x. I know we don't need to write that. I know the derivative of x is 1, but I think it's to your advantage to always think about when you're using the fundamental theorem of calculus part 1, even if you're just plugging in x, at the end of the process, you're going to multiply by what? Say the words. By the derivative of x. I plugged in x for each t, and then I multiply by the derivative of x. And no, I'm not going to write that usually. But the reason I want you to say that to yourself is because then, if you're plugging in something that's different than x, you will remember that you have to multiply by its derivative as well. So if we plug in the natural log of x here, our f prime of x is going to be sine of natural log of x squared times e to the natural log of x times the derivative of natural log of x, which is 1 over x. Excuse me. And that always is what's going to happen with the fundamental theorem of calculus part 1, is whatever your limit of integration here that has a variable in it is, whenever you use the fundamental theorem of calculus, which just amounts to plugging it in for each t, at the end of that process, you then multiply by the derivative of the thing you plugged in. And we can even make it more challenging by having both the bottom and the top have variables. If I wanted to find, say, the derivative of the integral from x cubed to cosine of x of 3t squared plus e to the t dt. We could do this the long way. You shouldn't do it the long way. The short way here is, what am I plugging in first, top or bottom? Always the top. Whenever you're doing a definite integral, whether or not you're taking the derivative of it or you're evaluating it and then plugging stuff in, it's always the top thing first minus the bottom thing second. So here, doing this the short way using the fundamental theorem of calculus part 1, which we should just say FTC, right? It's a lot. Saying fundamental theorem of calculus is probably a lot to write, a lot to say. So I'm going to plug in cosine of x for each t, and I'm going to get 3 times cosine of x squared plus e to the cosine of x. And then I'm going to multiply all of that by what? What's going to go right there? Almost, yeah, but it's negative sign because it's the derivative cosine, which is negative sine of x. Minus, then we do it again, except now we're plugging in the bottom limit of integration. So we're going to get 3 times x cubed squared plus e to the x cubed, all of that times the derivative of x cubed, which is 3x squared. And that is definitely what they want you to do when they give you a problem like this. They don't want you to do all the work I'm about to show you. So here's the explanation. But don't do this. Not that you can't write this down, you're welcome to write this down. Just when someone asks you a question like they don't want you to, so most of the time you can't do it the long way, but even if you could, you shouldn't. So let me show you what I mean. If we actually find this integral from x cubed to cosine of x of 3t squared plus e to the t, we're going to use the fundamental theorem of calculus part 2. What's the antiderivative of 3t squared? T to the third. What's the antiderivative of e to the t? Everyone's favorite, e to the t. And we're going to evaluate that between x cubed and cosine of x. So we're going to plug in cosine of x first. We're going to get cosine of x quantity cubed plus e to the cosine of x minus, then we're going to plug in x cubed, and we're going to get x cubed cubed plus e to the x cubed. And now we're going to take the derivative of all that, right? Because really, so I'm going to write the derivative in front of all this. We're taking the derivative of all that. The derivative of all that. The derivative of all that. Which is going to require extensive use of the chain rule. So the derivative of something cubed is 3 times our something squared times the derivative of the inside. Plus the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Minus, you could simplify this as x to the 9th, but I'm going to use the chain rule and say the derivative of x cubed cubed. Well, the derivative of something cubed is 3 times my something squared times the derivative of the inside, which is 3x squared. The derivative of e to the x cubed is the derivative of e to the stuff, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And then if we do some factoring, we can rewrite this as 3 cosine of x squared plus e to the cosine of x all times negative sine x minus 3 times x cubed squared plus e to the x cubed all times 3x squared. Which is exactly the same thing we got doing it the short way. So I really can't emphasize enough, right? We want to do it this way. We want to be okay with being like, oh yeah, I'm taking the derivative of the integral. I'm just plugging in the variable limit of integration. And then if I have to, multiplying by its derivative at the end. Actually, no, not if I have to. Always multiplying by the derivative at the end. Even if it's just x, multiply by its derivative, which is 1. You could even do it for a constant. Say, plug in the constant and then multiply by its derivative, which is 0. So you don't really need that part. It always works. All right. Yeah, okay. And then, yeah. So I think that's right. Fundamental theorem of calculus part 1. I don't think there's a lot more to say about it. Oh, actually I do. There's not, well, not, but let me throw one more example at you because I do think it's a good question. I tried to ask one like this before and my example was not the best, but here's a good one. So here's a question I could totally see someone asking on an exam and thinking like it was pretty good. Limit as x approaches 3 of the integral from 3 to x of the square root of 1 plus t squared dt over the integral from x squared to 9 of the square root of 1 plus t cubed dt. And if we were to plug in 3 for x, what kind of thing would we have? I know that's not a great question, but like if you plugged in 3 for x, what do you have on the top? 0. What if you plugged in 3 on the bottom? Also 0, because on the top it's the integral from 3 to 3, which is automatically 0. On the bottom it's the integral from 9 to 9, which is automatically 0. So this is definitely an example where we could use L'Hopital's rule. So this is going to be the limit as x approaches 3 of the derivative of the top. So that's the derivative of the integral from 3 to x of 1 plus t squared dt over the derivative of the bottom, which is the derivative of the integral from x squared to 9 of the square root of 1 plus t cubed dt. And then we take the derivative of each of those parts using the fundamental theorem of calculus part 1. So that's going to be the limit still as x goes to 3. The derivative of the top is not terrible. We plug in x and we get the square root of 1 plus x squared times what? The derivative of x. What's that? Okay, right? You don't have to write the times 1, but I want you to think about how you're always multiplying by the derivative of whatever you plugged in, even if it was as simple as just x. Not required, but I think good for you to do. On the bottom, same idea, except on the bottom, since the variable's in the lower limit, it's going to be negative square root of 1 plus x squared cubed times what? Thank you. And now we can just plug in 3 for x and get the square root of 1 plus 3 squared over the negative square root of 1 plus 3 squared cubed, so 9 cubed, times 2 times 3, which if you wanted to simplify it, it would be the negative square root of 10 over the square root, or 6 times the square root of 730. Because 9 cubed is 729. Okay, I think that's enough. It's also 4:30, so definitely enough.